Hello, good morning to all of you, and welcome to this course on. Uh, Hello, good morning to all of you. I think there is some miscommunication about uh, the class because I don't see any students joining the class today. Still, I thought that I'll record an introductory session on the course. And as all of you know, the course is about the fundamentals of nanoelectronics. I am Vishwendra Singh Punia from the Department of Electronics and Communication Engineering, IIT Roorkee, India. And it will be a pleasure to interact with you during the course. So before the next class, I would recommend all of you to go through this video and maybe come up with questions that you might have about the course or about the content that we discuss. So yeah, let me begin the course with the uh, background itself, with the right from the basics. So, uh, as all of us know, that electronics is essentially the story of conquest of electrons. What do I mean by the conquest of electron? Uh, I mean that almost all the electronic devices, or essentially almost everything that we do in electronics, is about controlling the motion of electrons or controlling the flow of electrons. So it is essentially playing with the electrons. And essentially transistors, as we know, are transistor essentially involves the controlled flow of electrons in a way. So uh, in electronics, what we essentially try to do is we try to control the electron current or the motion of electron according to our the need, according to our need or the application that we want to use it in. For example, in transistor, we want to control the flow of electron between two terminals by applying a voltage or current on the third terminal. That's what we try to do. So in my opinion, the way I start this subject is that in order to understand electronics or nanoelectronics, we first need to understand the nature of the electron, how the electrons behave. And I have been told that the class is about class is a PG class, is a master's class with a background in quantum mechanics, quantum electrodynamics. So I hope that most of you are aware of the basic nature of electron, which is quantum mechanical nature. But still, I thought that I'll go through the fundamental of quantum mechanical behavior of electrons, at least qualitatively at the beginning. So if we try to understand the nature of electron, what we will do is we will compare the behavior of electron with our everyday uh, life, basically what we observe in the real world, in the practical world around us. And generally, the properties of matter that we see around us, they can be broadly classified in two categories. One is the particles, second is essentially the waves. And in order to properly understand the nature of electrons, uh, Feynman actually proposed a thought experiment, which is very beautiful in explaining the quantum mechanical nature of electron, because quantum mechanics is nothing like what we see around us. It is nothing like the classical world. But ultimately, we need to go from classical world to a quantum mechanical understanding. So that's why we start with the classical objects. We start with understanding the particles, understanding the waves, and then we will try to understand the nature of the electrons. Okay. So, so this is the experiment proposed by Feynman, and this is essentially similar to the Young's double slit experiment. In this, so first of all, we have a particle source here, and let's say we have a particle gun in which particles are coming out in random direction, all the directions in a way. And uh, in front of this source of particles, we have a wall on which we have two slits or two holes essentially. Slit number one, slit number two. So these are small openings in the wall in front of the particle source. And then after some distance of the wall, we have what Feynman called a backstop, or we have a detector. So we have something which is detecting the particles that are coming out of the wall. Okay. So in this experiment, and by now you must have remembered that this is pretty much similar to the Young's double slit experiment. And in this experiment, if we try to measure the intensity of particles or number of particles as a function of position on this backstop on the detector on the uh, along the detector. So if we consider this direction to be the x direction, then uh, in your opinion, what would be the distribution of electrons on the backstop as a function of x? What do you think? So please take a moment and think about this. What will be the distribution of particles on the backstop as a function of x? So let me simplify this for you. So in order to understand the distribution of particles on the backstop on the detector, what we do is first we close we close one of the slits. Let's say we keep slit one open. We keep this open and we close this. So in this case, the particles are only moving through. In this case, particles are only moving through slit number one, and two is closed in a way. Okay. So in your opinion, what is going to be the, so only if hole one or slit one is open, then what is going to be the distribution of electrons or distribution of particles at the backstop? So I think this is easy to predict because what we can easily say is that if only slit one is open, in that case, P1 will be the distribution of particles on the wall, and in P1, we have a maxima right in front of the this hole. So as we know, so let's say this is a particle gun. So this is, let's say, a gun throwing classical tennis balls, let's say, and so the balls will go to slit one. They will be scattered at this slit and they will be thrown to the backstop in random direction. So in that case, the distribution that we can expect is, or this you can also maybe verify from a simple experiment in your laboratory, that P1, which is P1 is the distribution when only the first slit is open, and P2 will be the distribution when only slit 2 is open and slit 1 is closed. So P1 and P2 are the distribution of particles when only one of the slits is open. Now, the question is, what will be the distribution or what will be the probability of observing particles as a function of x on the backstop when both the slits are open? Let's say now we keep both slit 1 and slit 2 open. For classical particles, this is a simple thing. Now, the probability when both the slits are open is going to be P1, 2. And P1, 2 is essentially the sum of P1 and P2. So finally, this is going to be the probability of observing particle as a function of x on the backstop, P1, 2. And P1, 2 is the sum of P1 plus P2, right? This is the classical behavior. Any classical particle will exhibit this behavior in this kind of experiment. Now, let's say instead of the particle source, we do the same experiment with waves. So instead of this gun here, the gun that we have at the source, let's say we have a source of wave. Let's say uh, the source of sound wave or water wave, and in front of this source again the same thing. We have a wall with two slits, and finally at the backstop we have an absorber of the wave, at which when once the wave falls, it is absorbed. So now the question that I ask is, what is the distribution, or what will be the intensity of the wave at the absorber once both the slits are open? So again, take a moment and think about this. Uh, and again, to simplify this situation, what we do is we first keep this slit one open and close slit number two, and we try to see what is going to be the probability, or what is going to be the distribution of the wave at the absorber. So the distribution looks something like this again. So the intensity of the wave that we observe at the absorber is I1 when only slit 1 is open, and the distribution is I2 when only slit 2 is open, right? So in this case, but now the interesting part comes up. What is going to be the uh, intensity of the wave at the observer, or at the wall, once it is absorbed here, when both the slits are open? Please think about it carefully. I hope you know the answer, because this is exactly the Young's double slit experiment, and the intensity of the wave that we observe at this detector as a function of x is like this. So if we have a wave source instead of particle source, what we observe is we observe constructive and destructive interference of the waves as visualized here, and that's what we also observe at the backstop, or at the uh, far end of the experimental set. In this case, what we see is that at some x values, so first of all, what happens is once a wave starts from the wave source, uh, it reaches to slit number one, slit number two, and these two slits now act like independent sources of the waves. So they essentially start two independent waves, and then these two independent waves can have interference with each other. And on this right side, we have either constructive interference or destructive interference. This is simple wave mechanics. This is also true for any kind of classical wave source. Okay, and this is what we have the intensity pattern at the source, right? The mathematical description of this is that in case of particles, what we have is we have the probability distribution P1 and P2, and the net distribution is P12, which is P1 plus P2. But in case of waves, we cannot describe, or we cannot characterize the wave just with probability distribution P1 and P2. We need to characterize the wave with H1 and H2. H1 and H2 are the amplitudes of the wave, probability amplitudes of the wave, and the intensity of the wave is I is directly proportional to the square of the amplitude. So if only slit 1 is open, the intensity will be h1 square. If only slit 2 is open, intensity will be h2 square. And if both the slits are open, intensity will be h1 plus h2 square. So now, since we are taking h1 plus h2 inside the square, then this essentially accounts for the constructive and destructive interference. Now, this is the classical world that we see around us. This is the classical mechanics that we have. Okay. Now, what I told you is that ultimately we need to understand the behavior of the electrons. So, what if we do the same experiment with electrons? Okay, so now at the source side, we have an electron gun, let's say, which is throwing electrons in all the directions. In front of it, we have a wall with two slits. Slightly ahead of the wall, we have a backstop, like the previous experimental setup. Now, take a moment and think about it. What is going to be the uh, what is going to be the distribution of electrons along this wall as a function of x, let's say. So we simplify, again, we simplify this setup. First of all, we keep the slit 1 open, slit 2 closed. In that case, the distribution that we observe is P1. And if we keep slit 1 closed, slit 1 2 open, the distribution that we will observe on the screen is P2, right? When both the slits are open simultaneously, in that case, what is going to be the distribution? Can you make a guess quickly? So the distribution is going to be essentially exactly like waves. And that is why we call that all the quantum mechanical particles have a wave nature, right? And the reason is that in quantum mechanics, you might already be familiar with this. In quantum mechanics, what we have is each quantum particle or each quantum system is characterized by a wave function or a density matrix, but let's say a wave function, which has a probability amplitude. In this case, let's call it phi 1, phi 2. Phi 1 is the probability amplitude of the waves, electron waves coming out of slit number 1, and phi 2 is the probability amplitude of the electron waves coming out of slit number 2, right? And the net probability or net distribution of electrons at the backstop will be the sum of phi 1 plus phi 2 square. This is exactly like classical waves that we have around us. Okay. So with this experiment, what we can say is, or what we would tend to conclude is that that the electrons are like waves. But the story is not yet complete. The story is uh, we have something more to the story yet left. So now in the same experiment, what we do is we make a slight modification. Again, we have an electron source, we have two slits, we have a final backstop or final screen on which we can observe the electrons. But now, right after the slits, we have a light source. As you can see, this is shown here that we have a light source right after the slits. And what is the job of this light source? So once an electron comes out of slit number 1 or slit number 2, what it does is it collides with the photons coming out of the light source. So in a way, the electron is scattered, or the photon will collide, and we can essentially detect if the electron is coming out of slit number 1 or slit number 2. So in a way, in the language of quantum mechanics, we are making a measurement on electrons state right after it is coming out of the slits, right? In this case, what do you expect? What would be the outcome of this experiment, the same experiment? So again, if only slit 1 is open and we have a light source, the distribution of electrons on the screen will be exactly similar to P1. Let's call it P1 prime. And if only slit 2 is open, we will have the distribution of electrons to be P2 prime, which is also quite similar to P2. And P1 prime and P2 prime have a peak in front of slit number 1 and slit number 2, as is visible from the diagram here. Okay. The interesting thing is that if we keep both the slits open, when slit number 1 and slit number 2 both are open, in that case, the final observation or the intensity distribution of electrons will not be like waves. it will be like this, which is quite similar to the classical particles. Now, the important thing here is that uh, if we go back to this the experiment on the waves, this experiment. In this experiment, if we keep any measurement device here, anywhere here, it will not change the outcome of the experiment. The outcome will still be this. In classical waves, the outcome is always going to be like this. But with electrons, if there is no measurement of the electronic state happening, the outcome is like waves. And if we are measuring the state of the electron, the outcome is like particles. So, and this is quite weird because we do not see anything like this around us. So, what we generally conclude is that electrons' behavior is of dual nature. Electrons exhibit a particle behavior as well as wave-like nature. Or in other words, what we can say is that electrons have dual nature, or have electrons are neither like particles nor like waves. They are something else. We cannot compare them to particles or waves. They accommodate the properties of both depending on the measurement of them. So what this experiment uh, hints towards is that the classical picture to understand fundamental particles is insufficient. So we need to have a fundamentally different uh, kind of physics to understand the classical particles. And in electronics and nanoelectronics, since we are trying to understand or trying to control the nature, trying to manipulate electrons according to our uh, according to the need of application, we should properly understand this quantum mechanical nature of electrons. Okay, so and that's what we will do uh, in at the beginning of this course. The initial couple of classes might be on about discussing the quantum mechanical nature of electrons. Okay, so but before going into that, I would so again I always like to start a discipline with the history of the discipline because that gives us a big picture about that particular field. And so, a course on nanoelectronics, I would like to begin with the history of electronics itself, a very brief discussion on the history of electronics. So, the history of electronics can be roughly divided in three eras, essentially. So, the first of all, what we say is what we call is the so-called pre-electronics era. Okay, what do we mean by pre-electronics era? So this is pre-20th century time when the electronic devices were not there in the current form. What do I mean by electronic devices? The electronic devices are essentially start from the invention of the diodes uh, uh, because in a diode we can control the movement of electrons uh, in a definite way. But before that, we had many electrical uh, technologies, electrical engineering related technologies. And in this era of pre-electronics time, the one of the main achievements was the discovery of electricity, the discovery of magnetism, the technologies based on electricity and magnetism. So the AC motor, DC motor, and even the radio waves, the generation of radio waves, the detection, essentially that overlaps with the birth of electronics itself. So the pre-electronics era is the pre-20th century time in which we as a humanity were trying to understand the nature of electricity and magnetism and how to use them. And this is also the time when the unified theory of electromagnetism was given after a long period of investigation into the nature of electricity and magnetism. Okay, and at the advent at the beginning of 20th century, what we say is that that is also the time of the birth of electronics. And initially, the electronics was essentially about vacuum tube electronics, because it was the time around in early 20th century, 1902, 1904, the first vacuum tube diode was invented. In a vacuum tube diode, as I hope all of us know, that we have a, a glass tube with high vacuum. Inside the glass tube, we have two diodes, and cathode and anode. And once one of them is heated, let's say we heat this the first diode that we call cathode, because of the thermionic emission, because once we heat a metal, the electron's kinetic energy is increased, and that lead to the emission of electrons. So that will cause electrons to emit out of the cathode. And if we have a positive voltage on anode, it will attract the electrons emitted out of the cathode, and this circuit will be complete. But if we have a negative voltage on the anode, in that case, the circuit will not be complete, right? Because it will repel the electrons. Electrons will not be able to reach the other electron. So in this case, in this way, what we have done is we have implemented a device in which, depending on the polarity of the voltage on the anode, we can have current or we can block the flow of the current. Okay, so in this way, this was the first. That's why this is called the first electronic device. The vacuum tube diode is called the first electronic device because in this device we could control the flow of electrons according to what we need, according to our uh, uh, needs. And then soon after diode came the vacuum tube triode, in which, in addition to these two electrodes, we also had a third electrode, which which gave a good quality or good control over this flow of current between the two terminals. So I'll have some more discussion on this in the coming slides. Then in late 1947, the first transistor was invented, and it essentially uh, led to the beginning of the so-called the transistor era. And all of us know that the transistor is considered to be one of the most important inventions of the history, actually, throughout the history, if not just 20th century, because it has uh, changed the course of humanity in a great way, in a big way. The birth of electronics has revolutionized the birth of solid state electronics, the birth of transistor has revolutionized the development of computer science, the development of all fields of engineering, because nowadays electronics is used in almost all fields of engineering. Okay, so this is the time when the modern electronics started, 1947, early 1948, when first BJT was invented. So let me quickly also take you through a bit of pre-electronics era. In pre-electronics era, some of the significant names are William Gilbert, who was the first one to study electricity magnetism systematically. He produced uh, uh, many volumes of work on the properties of charges, properties of electricity. Then the second, and there are other names as well, but I'm just quoting some of the names. The Benjamin Franklin studied the nature of lightning, the thunder lightning that comes from the clouds. And then I would specifically like to mention the name of Maxwell. Before Maxwell also came Coulomb, Ampere, and many other stalwarts in this field who contributed in understanding the nature of electricity and magnetism. But Maxwell was the first one, or Maxwell ultimately, after the experiments of Faraday was actually a great experimental electrical engineering or physicist who had great intuition about the electricity and magnetism. After Faraday, Maxwell was the first one to put uh, the electricity and magnetism or the electromagnetic waves in mathematical forms. Okay, so so Maxwell initially gave 15 or 16 equations, which were condensed in 4 equations by Heaviside, and that is considered to be one of the finest work of uh, mathematical physics till date, because it was the first, or in that case, Maxwell was the first one to unify two seemingly distinct field of physics, the electricity and magnetism. So after the Maxwell's equations, we have an understanding that the photons, the light waves, the electricity and magnetism are essentially a unified field, essentially a unified. These are or light is just a vibration of electric and magnetic fields. Then on the application side, Edison was the one of the greatest inventor of many electronic appliances. Also, the DC light is attributed to Edison. Tesla uh, and Westinghouse were on AC light. Tesla was also a great uh, engineer, physicist who is responsible for the invention of induction motor AC transmission systems. Then Alexander Graham Bell, Elisha Gray, uh, they invented the telephone, which was based on the previous developments. Then Hertz was the one to demonstrate the transmission of the and detection of the radio waves along along with around the same time, J.C. Bose from India and Alexander Popov from uh, Russia, and also Marconi from Italy, they actually invented the radio receivers for radio communication. So generally, the invention of radio communication is attributed to Marconi, but it was done uh, at the same time. The important contributions were done by both Popov and Bose as well. Then, so this is a few of the landmarks in the pre-electronics era. Then came the vacuum tube electronics time, in which diode and triodes were invented. So in this case, so it was the time around 1904 when this diode was invented, and as I already told you, that it has two electrodes, cathode and anodes, and the current between the two electrodes was controlled by the voltage that we apply on the anode, right? So in that way, if the voltage is positive on the anode, it will allow the current to flow. And if the voltage was negative, it will not allow the current to flow. So if we apply an AC signal on the anode, only during the positive half cycle will the current flow through the circuit. And during the negative half cycle, no current will flow through the circuit. So that way, what we can essentially say that an AC signal which looks like this, which is an oscillation in positive and negative uh, amplitudes, using diode, it can be converted to only the positive half cycle signal. So in this case, this AC, this is the pure AC signal, and once we put it across a vacuum tube diode, it also has a non-zero DC component, because now the average value of the signal is not zero. Okay, so that way this is also called as rectifier, and this is considered to be the birth of electronics. And this was highly useful because it had many applications, because it could convert AC to DC. AC was used to transmit electricity to long distances. Most of the appliances were based on DC, so we always had to convert uh, the light coming from the transmission lines to the light that we need in the appliances, and that was done. So diode was one of the first components to be used as the rectifier, which is AC to DC converter. Okay, and soon after diode came the triode. It was invented in 1906 because it was a natural next level invention of uh, level invention. In this case, apart from the two diodes, we have a third terminal as well. And this third terminal is sitting between the two diodes. And now, if even if we apply a small voltage on the third terminal, what happens is that the amplitude of the current changes by a great deal, because this third terminal was closer to the cathode, the source of electrons. So it could control the flow of electrons in a much greater way, right? So, and the addition of the third terminal also gave more degrees of freedom. It also resulted in many more applications, because now the switching could be achieved. Switching means now the current between the two terminals could be switched on or switched off by just the third terminal. Also, amplification could be achieved. If we apply a small signal here, the signal that we get across the two terminals was big. So that way, switching and amplification could be achieved using this third terminal in the triode. So that way, triode was a great device, because apart from being a rectifier, it could also be used as a switch. It could also be used as an amplifier. And that's why using triode, many new applications could be came up, and so some of the inventions of the vacuum tube electronics era were rectifier, amplifier using triodes, radio communication technology, because the detection was done using the vacuum tube technology, television, radar, and even computer was made out of uh, various combinations of diodes and triodes. Because in computing systems, even now, what we generally need is we need switches. We need a lot of switches working in a coordinated way. And at some points, we also need amplifiers, amplification. So both of those things could be achieved using a triode. So it also, so this initial vacuum tube electronics era also led to some very important inventions in the of the modern times. Then, along with the invention of diodes and triodes, what we also had was that in the early 20th century, the photoelectric effect was discovered, and the quantum mechanical nature or the discrete nature of the photons was proposed by Max Planck. And subsequently, the quantum mechanics came up, and this actually uh, led to a huge shift in the understanding of the basic nature of the uh, basic nature of the material, basic nature of the fundamental particles. And then soon after, at the beginning of at the first in the first half of 20th century, came two world wars, during which the technological development actually was the focus was extremely high on the development of new technologies that could be used in war ultimately. So, and in this sequence, the development of electronics also saw huge jump. Okay, because during the World War, there was huge need, big need for computers and for radar systems, for or for all kind of technological, for missile guidance systems, or all kind of technological applications. And along the same time, 1930s, 40s, the quantum theory of solids also came up. So yeah, in 1920s, the fundamentals of quantum mechanics were being built up, but in 1930s, 40s, the quantum theory of solids, uh, which means how to understand the conductivity with quantum mechanics, those that theory also developed. And towards the end of 1947, the first transistor, which is essentially uh, an analog of a vacuum tube triode, was invented. Okay, so and this is the device that all of us are familiar with, and so I would ask you to sort of think about what is the idea behind a transistor. The idea behind a transistor is exactly like the idea behind a triode, in which transistor is a device in which we can do switching and amplification. We can make it as a switch, we can use it as a switch, and we can also use it to amplify the signals. And it's a three-terminal device. The essential idea behind a transistor is if we draw transistor as a black box, it has three terminals, let's say terminal 1, terminal 2, and a third terminal, terminal number 3. Terminal 1, 2, and 3. So the idea is that in a transistor, we can control the flow of current between 1 and 2. So the current between 1 and 2 can be controlled by voltage on 3 or current on 3. So the current between terminal 1 and 2 can be controlled by putting a current at the third terminal or putting a voltage at the third terminal. So there are two kind of transistors. One is in which this control terminal, third terminal, uses current to control the current between 1 and 2, and that is the BJT, bipolar junction transistor. In another kind of transistor, a voltage is used to control the current between terminal 1 and 2, and that is the FET. This is BJT and that is FET. So, are you aware of the name, or where does the name transistor comes up? I hope being a PG student, you might be aware of this. But let me quickly go through this because that way I like discussing these things because they complete our understanding of technical things, how the names come up, where the history is coming up, what is the story behind a particular invention. So the name transistor essentially can be broken down in two words. One is transfer, second is varistor. So varistor means a voltage dependent transistor, voltage dependent resistor. So, so a transistor is that a transistor in a way is a voltage dependent resistor in which the effect is transferred from a terminal to the two other terminals. In other words, this terminal number 3 can change the resistance between terminal number 1 and 2. So the resistance of R12, which is the resistance between terminal 1 and 2, is dependent on voltage applied on the third terminal. So that way we have a transfer effect, transfer of effect of voltage from terminal number 3 to 1 and 2, and it is a voltage dependent resistor. So that's why the name transistor can be understood. Another, in a way, another thought behind the name transistor is that it is a device in which we have a trans conductance or trans resistance. Because what do we mean by trans resistance? A trans resistance, or let me first simply tell you about resistance. Resistance is, in very simple words, voltage applied between two terminals, 1 and 2, divided by current between the two terminals. The trans resistance on the similar lines is again the current between the two terminals, but the voltage applied on the third terminal. Or to be more precise, the change in current between two terminals as a function of the applied change in voltage on the third terminal. So that is called as the trans resistance. And the transistor has this property of trans resistance, which means that the resistance between terminal 1 and 2 depends on the voltage applied on the terminal number 3, right? So, and that's why it's a varistor as well. So that's essentially responsible for the name transistor. Okay. So finally, the takeaway is the key takeaway is transistor is a three-terminal device in which we can achieve switching amplification, and the output across the two terminals can be amplified by applying current voltage across the other two terminals or other terminal. So there are two kind of transistors. One is BJT, second is FET, and historically, uh, the idea of FET, which is the MOSFET, actually that is quite old as compared to BJT. So the idea was itself given in 1926. But a MOSFET or a field effect transistor could not be invented for a long time because the interface effects are quite important in these kind of transistors. And the first transistor to be invented was a point contact transistor, uh, which was demonstrated in December 1947 in Bell Labs. And in after a few months, BJT was again demonstrated by the same group at the Bell Labs. Okay, and transistor as a switch is the backbone of modern computers. So this is the picture of the first point contact transistor. This group was responsible for the development of the transistors. This group was being led by Shockley, and the two engineers who were the first one to implement a point contact transistors were Bardeen and Breton. Okay, but that was not enough actually, because any real life application, for example, any decent computer, it needs a large number of transistors to operate, to do a practical, a useful operation. So, so the transistors could not be used for around next 10 years in a big application. But in at the time around in 1960s, at the beginning of 1960s, uh, integration was made feasible. Integration means putting a large number of transistors on a single piece of semiconductor, on a single chip, essentially, on a small chip. So that way, we can make a practical, uh, we can have a, a real life device with large number of transistors in a small size, right? And it was done at the beginning of 1960s, and 1968 Intel was founded, and that is the time when this field actually exploded. So after the invention of integration, after the integrated circuits were demonstrated in 1965, 68, around that time, after that, this curve essentially shows the trend of the development of this technology. So what we have is, on the x-axis we have uh, the year, right from 1970s to 2010. It's almost the same trend even now. And on one of the y-axis we have the cost per transistor. On another y-axis we have the number of transistors per chip. Per chip means this is like 1 centimeter by 1 centimeter area of a semiconductor, of silicon. So on this piece of semiconductor, uh, in early 1970s, let's say we had around 1,000 transistors, but now we have around 1 billion transistors on the same chip. Okay, and that is the rate of progress. This is almost like an exponential growth. And this trend has a special name, which I hope all of you are also familiar. This is called as Moore's law. And the law is essentially, it's not a fundamental law of nature. This is like a trend and a prediction of a trend. According to Moore's law, the number of transistors, Moore actually predicted that number of transistors on a single chip will double every almost 2 years, 18 to 24 months. The number of transistors on the same area of the chip will increase, which means the transistor density of the chip will increase, will be almost double every 2 years, every 18 to 24 months. And this trend has been going on since now last around 60 years, 50 years now. And but now, as we know, and this is this has become feasible because the the size of the transistor is continuously shrinking, and which is also reducing the cost per transistor, because in early 70s, the cost per transistor was around $1. Now the cost per transistor is around 10 to the power minus 7, minus $8. So the cost is decreasing at the same rate as the number of transistors are increasing on the chip. So, but now and this has become feasible because the transistor size is shrinking. Okay, so this is essentially the evolution of the semiconductor technology, and this is how a typical field effect transistor looks like. I hope all of you are uh, familiar with this. In a field effect transistor, what we have is we have a piece of semiconductor. We have a body silicon, p-type silicon as a body of transistor. On this, we have two contacts, the source and the drain contacts of n-type semiconductor. And in between source and drain, there is a small region, this region, which is called the channel region. On top of this channel region, we have an insulator, which is generally the oxide of the same semiconductor, silicon oxide. And on top of oxide, we have a gate, which is of either metal or polysilicon, or we can say that it is a conducting gate, the third terminal, and also known as the control terminal. So what happens in this transistor is that the current between the source and the drain is controlled by the third terminal, which is gate, right? And in this device, the most important part of the device is this, because ultimately the current flows between the source and drain in this small region of the transistor, right? And we also have the third terminal, which is also equally important, but since that is isolated physically or electrically isolated from the channel, so we can, in order to understand the nature of this uh, uh, device, we can initially, in a way, we can ignore this part, and if we first try to understand the electrical characteristics of this two-terminal device, in which we only have a source, a drain, and channel region. That is also, or that is the starting point to understand this important device in electronics. Now, the evolution of semiconductor technology has happened according to Moore's law, as all of us know. And in this uh, duration, what has happened is that the length of the channel, which is the region between the source and the drain, has shrunk to such an extent that it was around 10 micrometer in 1971. Okay, so we know that number of transistors per unit area is on the same chip is increasing, and which means that the transistor size is shrinking. So this length of the channel between the source and the drain is shrinking to a great extent. So in 1971, this length was around 10 micrometer. And in 1984, around 1 micrometer. In 2016, we had what is called the 10 nanometer technology node of transistor. It does not mean that the length was around 10 nanometer, but it shows the development. And the what is the distance between two atoms? The distance between two atoms between the atoms is generally in angstroms, which is a few angstroms. So which means it is of the order of this value. So what I'm trying to hint towards is that the because of this shrinking of transistor, now the length of channel is approaching the atomic dimensions. It is only, or in a way, in modern day, or at the moment, we have what is called as 5 nanometer technology. So initially, the name of technology was given on the channel length, but around at the beginning of this century, after uh, uh, 2010 or 2006, when the channel length was around 20 nanometers or 40 nanometers. After that, it was becoming difficult to reduce or to shrink the channel, actually. So indirect methods were employed to increase the chip density or to cut the cost and to have more number of transistors. So alternative geometries of MOSFET were employed. So, but the naming of the technology was done based on nanometer itself. So even the modern day technology is called 5 nanometer technology or 7 nanometer technology. But it does not mean that the channel length is 5 nanometer or 7 nanometer. Actually, this name does not correspond to any physical dimension. But what we can say is the distance between the two contacts is few tens of nanometer or 10 or 20 nanometer still, which is only a few tens of atoms or few hundred atoms between the two contacts, and which is still very small dimension. And that is actually the birth of nanoelectronics. So when the channel length, when the active region of the device, when this important region of the device is only few nanometers long, how does this device behave? How to make a transistor out of this device, or how to have the transistor action out of this device is the subject matter of the nanoelectronics. Okay, and that is what this course is going to be about. So my question to you is, what changes from this channel length, from a 10 micrometer channel length to 10 nanometer channel? Or what, how does the physics change once we go from 10 micrometer to 10 nanometer channel? In your opinion, how does it change? Just uh, take a moment and think about this. And that is essentially the question that we will be trying to answer in this course over next 1 month or so. Okay. So finally, what we have is we have a two-terminal device. We have a channel between the two contacts, the source and the drain. And the trend is that this distance between the two contacts is continuously shrinking as we are uh, progressing to the in time. So nowadays the distance is almost few nanometers. So in the early days, or generally what happens is that generally source contact is kept at ground, source is grounded. The drain, on the drain contact, we have a battery applied to it. So once we put a battery at the drain terminal, what it does is it will set up a current in the device, which means electrons will start from the source, they will go to the drain through channel region. And the current will flow from drain to source in the opposite direction, right? So one of the most important things to understand is how does electrons flow from source to drain when we apply a voltage on the drain terminal of the device. Actually, the name source comes from the origin lies that it is a source of electrons. It is the terminal from which electrons start, and the drain is the terminal to which electrons come to, or where the electrons are taken out of the device. So that's how the current flows in a transistor. But the important question to understand, or to important point to understand, is how does the or how does electrons flow from source to drain? Okay, so, or in other words, what is the transport physics of these devices? So what we can say is that in early 1980s, 1970s, when the channel length was few micrometers, around that time, an electron will start from the source, it will enter into the channel, it will collide with atoms in the channel, or it will collide with, maybe collide with other atoms, other electrons. And the motion of electron will be somewhat random zigzag kind of motion, in which uh, after multiple collisions, it may, so this is the source, this is the drain, it may lose its energy in the channel itself, and few electrons whose energy survive, they may reach up to the drain side. So this was typically the nature of the transport, nature of the electron transport around 1970s, 80s, or even in 90s. And this is uh, by keeping this nature in mind, most of the transport physics of electronics has been formulated. So that is how the conventional semiconductor physics has been formulated, that electrons start from the source, they go through multiple collisions in the channel. So after a zigzag motion, they go to the drain terminal. Okay. But after the shrinking of the channel, what is happening is that now the device or the channel length is so small. Now what is happening is the that uh, in a very small channel, the electron will start from the source, but the channel is so small that it will directly go to the drain terminal without any collision in the channel. And that is the scenario in 2016, 2018, or even now, actually. So now the nature of electron transport in the devices has changed fundamentally. In the in the previous century, the nature of transport was what was called as the diffusive transport, in which electrons undergo multiple collisions in the channel before reaching to the drain terminal. But now the device channel length is so small that electrons can directly go from source contact to the drain contact, right, without any collision in the channel. And this transport is called as the ballistic transport. So it is called ballistic because there is no collision. It is like bullet going from one side to another side, straight, without any collision in between. So now my question to you is, and this is where I will end today's discussion, how would the electrical properties of the device change if the nature of transport changes from diffusive to ballistic? So how would, let's say, the resistance change? So the idea of resistance in a conductor, generally the idea of resistance is that once an electron travels from through a conductor, it will collide with multiple atoms on the way, and after the collisions, uh, uh, it will uh, go to the other terminal, and that these collisions are responsible for the resistance. But in a ballistic conductor, there is no collision in the channel. Now, how would the resistance, or would there be any resistance in the device or not? Or how would the idea of resistance change? So let me ask you this and stop here. So please think about this. How would the electrical properties of the uh, devices change if the transport of electrons change from diffusive transport to the ballistic transport? Okay. Please think about this, and uh, we will have more elaborate discussion on this in the coming class. Okay, so thank you all, and I hope to see you in the next class, maybe in a more number. Thank you all. Bye bye.